It's my pleasure as head of the Department of Materials to warmly welcome you to this special event this afternoon. Before I say a few words about what's going to happen, I should point out that in the event of an emergency alarm, the fire exits are the doors at the back that you came in through, and also this door to my right here, and please do make your way out of those calmly and swiftly should the alarm sound. We're here this afternoon to celebrate the achievements of an exceptional individual, Professor Natalie Stingelin, who began her academic training at ETH Zurich with a degree in materials science and engineering, followed up by a PhD on the microstructuring of polymers and polymer-supported matter with Paul Smith. Since then, she's worked at a variety of esteemed institutions, including the Cavendish Laboratory at the University of Cambridge, the Philips Research Labs in Eindhoven, and Queen Mary University of London. She arrived here at Imperial in the Department of Materials as a lecturer in 2009, and with typical Swiss efficiency, she has been rapidly promoted, becoming Professor of Functional Organic Materials in 2014. Natalie is in very strong demand internationally to speak, so we're looking forward very much this afternoon. It's not for there's more than one reason why Natalie has a reputation as a high flyer within the department, but we've been looking forward to this inaugural lecture for some time now, so we're delighted to hear about cool plastics for a greener world. I give you Professor Natalie Stingelin.
Thank you, Peter, very much. Thanks for everybody to make the time and come here. My family, my friends, many from North America, students and colleagues. So I want to talk about plastics, cool plastics, plastics for a greener world, and I want to go through a few examples how actually plastics, hopefully in future, can help us and our Earth. Because nowadays, sometimes you only hear bad things about plastic. They got a bit of a bad reputation, and usually what many people attribute to plastics is they pollute. They end up in our mountains, they end up in our rivers, they end up in our oceans, and therefore, especially recently, you see more and more news articles warning us about plastics. But plastics are actually not that bad, and why they pollute is because they're everywhere. I can't say really look around here because this is a very old classic lecture room. But if you take your office, your home at home, and you would take everything that is made of plastics out, it would be pretty empty. You see them in shops, food packaging, containers, furniture, your car, toys, everything is made of plastics. And therefore it's not surprised that even musicians thought about the plastic age, and that was already in the 1980s, a few decades ago. Plastics are indeed everywhere, and many things we couldn't do without plastics. I grew up in the Swiss mountains, as many of you know. I mean, if you look at skis, how they developed, I mean, I wouldn't say we would have wooden skis as kids, but it was close. Nowadays, they're high-performance plastics. For those who are maybe not so used to the cold areas, but maybe the more warmer areas, I spent 1 week at Hawaii for the Pacific Chem, one of the biggest chemistry congresses, and it happened that it was the Billabong pipeline, I think it was, competition. Really stunning. Clearly, you need also the skills. But what would they do without newer, stronger, and lighter plastics? And that's in particular true, I know we have some sailing friends here in the audience, for sailing boats. Ultra strong, but ultra light plastics really make it happen that the Swiss actually sometimes won. Alingi. I know it's ridiculous, we are a country without ocean, but we won the Americans' Cup. The reason is, the more weight you actually gain, meaning the more weight you lose in the sails, you can put down here, and therefore it makes the sailing easier. One person who dramatically helped this process is Paul Smith. Paul Smith, actually, he's Dutch. In the 70s, he invented the strongest fiber on Earth by density. It's made out of polyethylene, and I have my little gadget here. I should not forget. All of you know polyethylene. They're really everywhere, and possibly this one material that pollutes plastic bags. Not very strong. But Paul, together with his friend Pete Langstra, figured out a way to make this type of material, polyethylene, super strong. He is also actually really the person who not only told me whatever I know in plastics, but because of him, I actually ended up in academia. I always wanted to go back home because where I grew up, there's a big nylon producer. And when I was studying, and that's for the students, I thought, well, why don't I study material science, because then I end up in entanglments. Because of Paul, things somewhat changed, and you see where I ended up. Imperial College in London, possibly not a bad choice. And really, polymers, we can really use them to fulfill visions. Literally. I mean, this was the first imagined, designed wearable. Perhaps functional, perhaps visionary, definitely not very comfortable. But nowadays, with the upcoming of conducting, semiconducting plastics, these type of wearable devices really become real, good reality. Airables, my brother is a technology freak. He already looks at the web pages when the airables become reality. And possibly in the time of new Star Wars, the androids the droids are still depicted as these metal species, but in case we start to have conducting, semiconducting, light-emitting plastics, we will have these robots essentially looking like us with skin very identical to our hand. And we came far. This was the very, very first transistor invented in the Bell Labs in the 1940s by Bardeen and Pertain. This is really the key element, or one of the key elements, that now is in every single iPhone, smartphone, computer, but we can do more. Nowadays, because we have these functional plastics, we can think of plastic electronics, bendable inverters, printable, that was too fast, printable solar cells that you print like newspapers, or light-emitting diodes that hopefully are the size of our hand, but which we can spray on windows. And one person that really drove this technology, Sacco De Leo, sitting here in front, really one of the pioneers of the plastic electronics area, with whom I really had great fun during my Phillips time, and taught me actually to enjoy the science. And therefore, because of these new types of polymers and plastics, it's no wonder that here at Imperial College, we have the Center for Plastic Electronics, meaning using these new plastics for good purposes. And the director and founder is also here, Professor Donald Bradley, commander of the British Empire. It's not a joke. He is. It's possibly Donald to blame, I would say, that I'm here. He brought me to Imperial, made Imperial College attractive, which was a step change in my career, and I have to thank. I also have to tell him off, though, because he works here in the glove box without lab coat. The other person I worked with a lot here at Imperial College is Paul Stavrinou. Thanks to the new types of plastics we have, we not only have the Center for Plastic Electronics, but underneath its umbrella, the Doctoral Training Center in Plastic Electronics, Paul has been a fantastic director, but also he taught me about photonics. I tried to teach him polymers and phase diagrams in return, so it has been and will be a very good teamwork. So talking about plastics, what are plastics? We sometimes call them polymers, and the reason is plastics are made of these long chain molecules. So you can imagine them like being spaghetti. And actually Gary mentioned it yesterday, so he sort of took my joke away. But they are spaghettis. So look at this schematic. So this is a real polymer. In case they're not made up of these long chain uncooked spaghettis, they get smaller and shorter, I have to say shorter and shorter. You possibly can see already from these schematics, properties will change. So these are tough. So they're really plastics because they're plastically deformable. Versus these guys, their chains are not interconnected, so they're brittle. And therefore the properties change as mentioned, and this is part of my first experiment, which hopefully will work. So this is a plastic, macroscopic. And because you have these long chains that are entangled, have knots, whatever, you can actually stretch them out, but you have some resistance. So you see, it's not so easy to pull these molecules on the macroscopic scale apart. However, when you have these shorter molecules, maybe still long chain in relation to other materials, you see there's no resistance. I can push them apart, and therefore they are very, very brittle materials, like candle wax as an example. But polymers are also very complex. And it's actually amazing that they're everywhere. They're not simple structures. So just look at this schematic, and you sort of can see it already up here too. You have some ordered part. Actually, I should start with the unordered part. You have some unordered part. But you also have bits where these actually long chain molecules align. And therefore, the properties change between these areas. But what we experience in the plastic project is the overall property. And as mentioned, then you have these knots. Today was so windy, I think everybody with long hair will have trouble tonight because they just form these intertwined structures. What also makes plastics so different to many other properties is they're highly anisotropic. Anisotropic meaning they have different properties in different directions. So along the chains, we have strong covalent bonds. So usually they're made up of carbon and carbon. So that's very similar, like in diamonds. In diamonds, you have only carbon dependence, and diamond is made up only of these strong bonds in all three directions. That's why it's so hard, so strong. What is different between the polymers? The polymer have these bonds only in one direction, along the chain. Perpendicular to the chains, they are made up with weak secondary bonds. And that's why polymers are so different than diamond. Weak secondary bonds means van der Waals bonds or hydrogen bonds. To give an example, again, polyethylene. Garbage bags, nearly, I would possibly say 70% of the plastic products are polyethylene. It's a material only made up of carbon atoms, here in black, you don't see them so well, and hydrogen in gray. And these weak bonds come because the hydrogens here interact. If you take a polyamide, nylon, you have a bit stronger bonds between the chains, hydrogen bonds. And they happen because sometimes you have also an oxygen or nitrogen here, and you form some links, some bondage between these atoms. Very, very similar like water. So therefore, while in one direction you have very strong material, in the other one they're weak, and the chains can slip, making the polymers very, very special. So knowing that at the end, polymers are a mess, what can you learn? Obviously, they must be useful because they're everywhere. Well, now let me give an example. Also how we can use them for hopefully a greener world. Charge generation. What does this mean, charge generation? It means you can actually sometimes use these materials for solar cells. You shine light on, and you create electrical charges, electrons or holes, electrons being negative, holes positive. And one of the materials we often use, sort of as a fruit fly, we test everything on it, is poly-3-hexylthiophene. So it's this material, carbon-carbon-carbon bonds, SO, but you have here a sulfur in yellow, and then you have these greasy side chains hanging, dangling off, which make the material soluble and processable. And here I have to say, I have to thank the chemists I worked with over the years, Martin Heaney, Ian McCulloch, John DeMello, despite he's a physicist, but he makes materials. And two partners in crime with looking at the charge generation are actually here. Professor Barry Rumbles, who famously said, I have to tell it again, 2009, if I talk about polythiophene again, you can shoot me. Well, obviously he survived. He still talks about P2H3, and working with him was crucial to learn how this very complex plastic structure can be used to learn about this charge generation, important in the solar cell process. The other person we always work with is Carlos, here in the pink shirt, heavily supported by Eric Bittner, and I will not comment on the guitar in the back. And Eric is an excellent guitar player, so not only a scientist, playing actually with the people from CC Top, which is quite cool. But let's go back to plastics. We have these complex structures. So how can we learn how these charges are generated? What happens when we have a sun, maybe not here in England right now? We shine light on our structures, and what happens is we create excitons, hopefully, S. What does it mean? Exciton is like a pair of electron and a hole, so a negative charge and a positive charge, and because they have different polarities, they're sort of like each other and are very close to each other. However, sometimes this exciton happens at this very, very disordered structure where you have disordered region, like down here, but then you have this a bit more ordered structure. So what happens is, then the positive charge, if it happens here in the ordered structure, can get separated from the electron. So suddenly the hole is sort of on a highway and can actually easily move to this side, versus the electron is stuck in central London traffic. But what happens is the charges get further apart. Our physicist friends call that a geminate polaron pair. Once this happens and the hole can separate a bit from the electron, of course eventually you find another electron. So you have again a negative charge, a positive charge, and what happens is they get closer again, together. Eventually they get so close that they recombine, so essentially the positive charge, negative charge, neutralize. That releases energy and you get photoluminescence. So essentially light is emitted. So these are very complex measurements Carlos did. It sounds possibly relatively easy, but he measures at what time light is emitted. And for the photophysics people in the audience, what it means is you create an excited state, so you have these charges, the positive and the electron, the hole, they immediately combine in case they end up on one of those ordered or unordered areas. But in case they're at this interface, you can separate them further, and it takes much, much longer till they come back. Okay, that's very, very much detail. Why do I pound on it? Very important when we afterwards go and make solar cells. Because when we make solar cells, and this is beautiful work by bioelectric. This was actually an exhibition at Expo Milano, I think Carlos went there, where they tried to use plastic solar cells and integrate them in architectural features. Here in England, you possibly would use that as a rain shelter. In other countries, you possibly would use them as a sun shelter. They also have ideas in North Africa to integrate these solar cells into the roofs of buildings. When this happens, clearly we need to have the efficiency, but we also have to ensure that all of these solar cells are of the same performance. So we have to create solar cells at a high yield. And therefore, we have to know what structural features we need. When we print them, like newspaper printing, at the end, little things, temperature, etc., will change, and will change the amount of those ordered areas, unordered areas. So we have to know what we require to get eventually these structures in multiple versions and at high yield. But we also have to take, and therefore I have to come back to plastics for the green world. So we can create solar cells, we can use them for harvesting energy, and actually also have different functions. But we also have to take other structural features into account. So we learned now about how important ordered areas like here and unordered areas interact, but what happens when we orient those chains? Because then, as mentioned, at least in this direction, we only put carbon-carbon bond. So in this direction, it looks like we have diamond. Obviously, in this direction, it's different. So this will be tough, but this material in this direction will be ultra strong and ultra stiff, like diamond. So how do we get there? How do we get from this disordered mess to something that is highly oriented and ordered? And you can imagine, you just have seen the experiment. When we have the melt, and they're like these cooked spaghettis, it's very, very difficult to draw them apart. The spaghettis, as shown before, they resist. It's not easy to stretch them out, and eventually they break. So how can we actually fully orient those structures? So the key is here, you just add solvent. You add a liquid. And the more liquid you add, you see that you have less and less of those long chain molecules per chain. And if you do that for a long time, add more solvent and more solvent and more solvent and more solvent, you see what happens, you can overdo it. So now at this point of time, you see this molecule is isolated. So you get in trouble when you stretch, because if you put some stress on here, this molecule here will not notice it. And eventually you have entirely isolated molecules. This will be brittle. But if you do add exactly the right amount of solution, you see what happens. So you have exactly enough entanglements that when you stretch this molecule here, because of the knots they have, this molecule down here, notice it too. And you can actually stretch it many times. And let's see, I have a demonstration how effective this is. It's again polyethylene, like this material. This material is melt processed, many knots, and you see it will break very fast. Now, from my friend in Sweden, now I have to be careful, one side is hot. Christian Müller, I've obtained polyethylene that is like this schematic up here. I move it a bit. I test the temperature. I have this clever app on my iPhone, because obviously you don't want to melt your material, if I can log in actually. So let's quickly check the temperature. Should be 120 or so. It doesn't like the metal. We tested it before. Well, let's assume I trust Albertino, he measured it before. This should be 120 degrees. That's a shame. I would have needed to ask Martin. He's much better with these apps. Anyway, this is now a piece of plastic, also polyethylene, like this bag in my pocket. And now it has exactly like 3 entanglements per chain. And now you see it. You see it's like 3 fingers long. Now I heat it, but not melt it, I just heat it without burning my hands. And you see, very, very long polyethylene molecules. And what I do now literally is essentially stretch on the molecular level these molecules out. This goes on for a while. I could do that for maybe not hours, but many minutes. And stretch and stretch. Actually, because I stretch, the temperature goes up. So melting temperature goes up. And now you see how nicely. That's how high-strength fibers are made. Oops, that was not too hot. But you see, from something that was 3 fingers long, you could go there forever. And to prove that I really stretched out the molecules, now I try to melt it, not too hot. And then you see, on the molecular level, because I melt it, it crumbles up again. So you go from cooked spaghettis, but with a lot of salsa, essentially, for the Mexicans in the audience, to uncooked spaghettis, fully oriented, and now what I do again is completely crumble them up. And if I would not have broken it, it would have gone to its initial state. Actually, I should show it maybe here. So we started with this and completely oriented them. And once I molten them, they crumble up again to their initial state. And the person who really invented this process is the person I mentioned at the very beginning, Paul Smith, who taught me polymer science. Why is this so important in the context of being plastics? Clearly, it's not only boats. Wherever you have lightweight, strong materials, you can use them in structures like that, like the Pathfinder Plus. Cars, the Pope Mobile is made of this polyethylene, and it means because it's so light, you actually save on petrol. You don't need so much petrol. So making something strong but ultralight helps, again, to produce a greener world. But it's not only about order. Also, disorder can be good. Because if you have something very disordered, you see it seems like a very homogeneous material. Despite it's a mess, it has everywhere sort of a good density. Versus when you have parts that are highly ordered, and you see that a bit here, these parts would have a different density than these unordered bits. And where that's important is, for instance, light. If you have a highly disordered material, light, we'll see it as something very homogeneous, and therefore it will not scatter light. So you possibly still used to CD boxes. They're transparent because they're made of polystyrene and amorphous plastic. Or you know PMMA, plexiglass. It's actually called glass because it's amorphous, but it's a plastic and it's transparent. So usually these disordered polymers, plastics, are used for optical applications. So they are in signs, CDs, possibly nowadays old-fashioned, but also where you definitely use the soft properties of plastics. It's contact lenses, where you definitely don't want to have some light scattering, you want to have a good view through them. The question though is, what we ask in my group, with many of our collaborators together, can't we go smarter? Can we really only use these type of disordered plastics for such applications? And obviously we can. Imagine, that's where we started in the 40s. The first transistor, the first electronic switch, the first electronic amplifier in this sense. But what then we can actually, instead of using electrons, or holes if you like, if we can actually use light. Why light? Light is faster than electrons or holes. Because you have something which is photons, light particles. Much easier to manipulate, and we can do everything we can do with devices like the transistors and other electronic devices. With light we can transmit. Obviously, I have here some party gadgets. Here we transmit light, and you could actually imagine, I'm not very good at this, my cousin is much better. He showed me actually how it works yesterday, so high tech. Waveguiding, yeah? So in principle you could shoot light in and it would be stuck here in this tube and go into the other direction. So light is actually clever. We can amplify signals, we can detect signals, we can modulate signals, integrate. And what else we really can do, actually, Paul Stavrinou, I showed the lovely picture in the red gown, is teaching me and my group. Though to actually use light, obviously, we need to manipulate light, like in these party gadgets. And often, we need to bend light, like here in the prism, somewhat reminiscent of the Pink Floyd album. And we learn how to bend light, or the key property to bend light is the refractive index. So just to show what is the refractive index, how can we show the effect of materials which have different property in this respect. So refractive index being a sign of how good or bad you can bend light. And here now I have to be careful again before I will burn myself. Good. So I have here 2 transparent liquids. I just want to say it's a kind of magic. And let's see if it works. Maybe not. Okay. And I have to see. So one is water, one is glycerol. 2 liquids. And I have here 2 magic sticks. And I have to turn this a bit down. Let's start water. And water has different refractive index than these 2 sticks. So now I put 1 stick in. You see there, why? Because the stick it's down here. I just don't want to spill it. And then the second one, and I hope you can see both of the sticks. Here is one, and here is one. Okay, you see the sticks because both of them have different refractive indices than water. So now I go to glycerol. Glycerol, very similar to alcohol. Bit more alcohol, actually, OH groups, alcohol groups. And one stick has exactly the same, well, close to a refractive index than glycerol. So I first start with the first stick, which has a different refractive index. I put it in, and you see down here the stick. Now I take this magic stick, which has the same refractive index as glycerol. And now you see I put it in, I hope you see. Oh, you still see it. No, see, you only see one stick. One is not visible anymore because the refractive index of the blue magic stick is essentially the same versus this one, the red stick. I mean, I call it red because the end is red. has a different refractive index. So you see this stick, but you don't see this one, despite I move it, hardly. You only see it getting in, but on the bottom, it's gone. So refractive index shows you how light is manipulated. So how can we use this with new types of plastics? Because while we only use currently plastics for contact lenses, CDs is this property which shows you how light is spent. You have with most of the plastics very, very similar refractive indices. And as I showed, actually, well, I hope it was somewhat clear, it's often the difference between refractive indices that it's different. So with the magic one, we had magic stick, it was the same refractive index like the liquid. You don't see it. The bigger the difference the refractive index is of the stick with the water, the better you see that stick. So that's why in photonics, so when you make devices with light, you usually work with inorganics. And I know Adam doesn't like this graph, because with inorganics you can cover nearly every refractive index range. So you can use a high refractive index inorganic material, inorganic meaning a ceramic, silicon dioxide like glass, titanium dioxide, or you have in your paint. And when you have a high refractive index difference with an organic, you see massive difference, light is massively bent. But as we know, these type of inorganic ceramics are so often are not easy to process, versus plastics, very easy to process. That's why they are everywhere. So how can we circumvent that? And obviously many, many groups in the world do that. We just can combine an organic with inorganic materials. So they are called nanocomposites or composites or hybrids. What means that? Nanocomposite, for instance, you have inorganic nanoparticles. So these black dots are made of lead sulfide, doesn't matter really what it is. The light part is the polymer matrix, it's polyurethane, like you have in mattresses or so. But you see these particles are in the range often of a few tens of nanometers to 100 nanometers. So we get sort of to the wavelengths of light. And that's why they scatter. So it's not the best picture afterwards, you will show it. It's films of these nanocomposites. And you see they're whitish because they scatter light. So we decided in my group not to go via the nanocomposite pathway, but we wanted to have inorganic species in a plastic so we can process the material as a plastic bag, a plastic bottle, whatever. And that was really a collaboration. Manuela found the material, and Walter Caseri can't be here today. He has to teach at ETH Zurich. And rather than making particles, you see what we try to do is really mix them on the molecular level. So we have metal or other inorganic species combined with polymers. So we always make these signs to show these are long spaghettis, and simply tells you then how many times this is repeated. And because you really mix them on this molecular level, calling them molecular hybrid, you see now when you make a film, you don't have scattering anymore because this mixing is on the very few nanometers level. And again, very different than in case you would take all these titania, oxygen, and making particles out of them. And now you see we coated this so we can use very, very standard coating technique. So this is a piece of plastic. We coated here this high refractive index hybrid. And you see already, despite this is a plastic at the end, it looks already like very, very metallic. It reflects much more. It reflects more because we increase the refractive index. And Eddie was here before, and I'm not sure if he still is around. But what you see here is depending on how much titanium species we put in our polymer, we can change drastically the refractive index. So we can go from a typical polymer value close to values we would get for an inorganic species, and we can change that also with temperature. So we can cover essentially the regime from 1.5 to 2.1. The numbers don't really matter, but it's really to show we have now a plastic that optically behaves nearly like an inorganic. So how can we now produce objects that can manipulate light? And the simplest is to stack them. So it's very similar, and I hope this animation works, like in a PET bottle, where we stack multi-layers, some to keep air out, some to keep the liquid in, some to give it toughness. So very similar, we now just stack different materials to get different functions. And you see here, so we have a high refractive index material, looks like this. Then we add a low refractive index material. This is also a plastic with a lot of, it's similar to Teflon actually. Then you get this, and then you go 3 layers, 4 layers, 6 layers, whatever. And what you see, despite the individual layers are transparent, suddenly the film gets blue. It gets blue because of the refractive index differences, similar like in the experiment I just showed. Sunlight gets actually not transmitted, but at these interfaces between high and low refractive index gets reflected. This is a graph I stole from Envistr's thesis, actually. And these multi-layers we call distributed Bragg reflector. They are actually mirrors, but not made with metals. And nature uses this all the time. So the Ulysses butterfly, beetles, they use these optical effects. And they get color not because they have a dye in there, because of the clever usage of refractive indices. And now when we start to stack them, we can really precisely measure how much or what color is reflected. So we can measure transmission. So we take a slide like this blue slide we showed before, you shoot light in, and you measure essentially how much light gets through. So there's always some scattering, so you never have 100%. But then you see, the more layers you have, the more you reflect. So here we have 13 layers, then we get to 21 layers. And here you get a system that is made with plastics, but at some given wavelength, reflects nearly all light. It's nearly a perfect mirror. And actually the color it reflects, so here, you can tune by the thicknesses. So if in case we want to have purple reflected, we go to thinner layers. And if we want to go to a red being reflected, we go to thicker layers. And indeed, you can play this game even further. And then we can start to reflect infrared. And that's where my other experiment comes in, designed by Matt Dyson. Because when we can reflect infrared is heat. And we can cook an egg by concentrating heat, by having mirrors that assemble heat. Here we still cheated, obviously, and we use aluminium. But imagine this would be made of plastic and transparent. And you can just injection mold it or whatever. And just to show that this works, here I have an egg. Uncooked. Now we put it into our, I have to take off the other one, into our magic heater, and we cook now the egg. Having this heat mirror now made of aluminium, and hopefully the egg is cooked. Actually, Matt tried with this black one before, so it should work. Let's touch wood. So instead of actually now manipulating light, we manipulate heat, which is actually also just electromagnetic wave. And here is a mirror that Andy was building very, very early on. Esther in the audience and my collaborator, Marcial, often use it now, which means we just make these individual stacked layers thicker and thicker. And what happens then is you see this infrared light around 1,000 nanometers is reflected. So you measure transmission, and then suddenly there's a bump where infrared light is reflected. A heat mirror. And what is spectacular, actually, we make a mirror that is visible for us as human beings. So we create a transparent mirror. So we have a mirror that the visible light gets through, but infrared light, the heat, is reflected. So why is that so important? For my collaborators in Saudi Arabia, I mean, what if you could now use these mirrors and put them on greenhouses? Maybe here in England we try to keep heat in the greenhouses, but in case we could use the desert to actually build greenhouses, grow food there, if we have these heat mirrors, we prevent the greenhouses to get too hot so that plants can't grow anymore. So here we can now use these clever plastics, not only for producing energy, help with a greener world, but also food supply. And maybe coming from the mountains, we can actually start thinking of this building. This is a picture, I have to say, I got from internet, of a thermal solar collector, where they actually also collect heat to afterwards gain energy. Coming from the mountains, you definitely don't want to have such an ugly building there. But can you imagine when we can make them with a transparent material, so we still can see through, we see our beautiful mountains, but the heat is reflected exactly where you want to. So it will not destroy nature so much. But obviously, we can also start now to think of heat guides, wave guides, like these little things I showed before. So what happens when we can start manipulating light, shooting light in here, getting it out of here? And here we cannot use stacks, but we now make essentially stacks in 2 dimensions. So here is a waveguide, a photonic waveguide, made in silicon, I think, so an inorganic material, a ceramic. And what you see here, you have these dots. So instead of the layers, you have dots in your material, so low refractive index, the dots, which is just air, and then around it you have the high refractive index matrix. Meaning, in here, some wavelengths, like in our mirror, are not allowed to go. So you can shoot light in, and actually you can bend it over corners. So you can imagine, when we could do that with plastics, we can make that similar like in our security features on the credit card. We can actually dump into these waveguides other structures to give them different functions and really start to go large area. So can you imagine, in case we would be able to collect light, but then using our waveguides, photonic waveguides, and guide the light into the cellar. Kevin and Stefan, co-supervised by Paul and I, look into it, and the key, of course, is when you have these structures, how far, it's actually this picture, how far can you really guide the light? Can we go 1 centimeter? Can we go 10 centimeters? Or can we go over meters and really actually guide light or heat in case it's infrared, like we now plumb water through our building? So in case we really manage that, obviously we are in the baby stage, I guess, right now, the potential is enormous. So we can use smart plastics to keep heat in when we want, like today, heat out, like in the desert, but also save energy by not using so much light, because we can harvest the light that is outside and guide it where we want. And the nice thing is, these materials that Manuela and Walti developed are made of super simple ingredients. They're made of titanium dioxide, which is used always, well, sort of titanium dioxide, in paints, and a polymer like polymer alcohol, which we use in glue and biomedical applications. So with that, I hope to show we can use plastics very, very beneficially. They're really not as bad as we often think. And those who remember, very, very famous film, The Graduate, 1967, when The Graduate was told, there's just one word, plastics. And I think as true as in the 1967, it is true in 2016, and we can hopefully change the world and change it to the better. Cool plastics for a greener world, hopefully. So with that, I thank really everybody in my group that have worked here. I know a few came actually back. Pleasure to see my collaborators in all the universities. I have worked, my overseas collaborators who made that trip here to England, rainy England, and family, students, and thank you very much.
Thank you, Natalie. It comes from me to give the vote of thanks. I'm Gary Rumbles. I'm from the National Renewable Energy Laboratory in Golden, Colorado. I'm one of the few people here from overseas. We have people from Cyprus, from Saudi Arabia, from Montreal. I'm trying to find Carlos, who's here. From Houston, which is like another country. Before I put some words down about vote of thanks, I thought I would go to Donald, because I knew Donald had given many of these. And I said, Donald, what's the vote of thanks all about? He said, oh, it's really easy. So you just thank people and be funny. And I thought, that's a bit ridiculous, because it's very hard to be spontaneously funny. So I went on Google and found a really nice outline of a vote of thanks, and it basically said, thank everyone and be funny. So here we are, having to be spontaneously funny and thank people. So the first thing I'll do is thank you for attending this lecture. Interestingly, the vote of thanks said you should always thank the audience because they think they're the most important people in the room. So you now feel all very humble because I thanked you. But I am thanking you for attending this. When you think of what it means to become a full professor, it really is, it's not the end of your career, but it's the end of a long, hard struggle through academia. It starts with 5 years of age, and you work through school, you go to university, you get degrees, you get PhDs, you then decide to become an academic, you move up the ladder, and really, it's not the end of the journey, but really it is a measure of your success to become a full professor. And Natalie has done that in an incredibly short period of time. And when I was looking at her CV, I realised that she started this process when she actually got her PhD in 2001. That is really, really a short period of time. And in 2001, I had actually left Imperial College, let alone come back. I've come back many, many times. But 2001 to 2000, I think she was officially a professor in 2014. That's really, really quite remarkable, and she should be very proud of that. And it's very nice that her family's here. Her mum, her dad, her aunt, her cousin, they're all here to see what Natalie has been up to. Her brother actually would like to have been here, Marco. I contacted him by email, and I said, you know, Mark, can you tell me a few stories? And he told me some fantastic stories. And I thought, I don't have time to put all these in, you know. It was really, one of them was an absolute classic. So if you buy me a drink afterwards, I'll tell you the story about the cakes. But let me tell you how I first met her. It all starts actually back in the 90s, the last millennium in fact. Donald and I worked in the field of plastic electronics, conjugated polymers, whatever you like to call it. And he said to me one day, he's always a very wise person, he said, you know, the problem with this field is what we lack is someone who understands polymer physics. We don't have anyone that does polymer physics. This is really, really lacking. We know, what do we know about it? It's like uncooked spaghetti is basically what he said. And I said, ooh, I'll write that down, uncooked spaghetti, I never thought of that. And then many years later, probably 10 years later, I was at a Gordon conference at Mount Holyoke in Massachusetts. And this college was a liberal arts college. It was stuck in the middle of nowhere, although people from Massachusetts wouldn't say it. And it was unbearably hot. I think you were there, Jenny, as well. It was unbearably, stiflingly hot. And it had only 3 places that were air-conditioned. The lecture theatre, library, well, we weren't going to go there, were we? And a bar. At the end of the high street was it was stifling, not stifling cold, just freezing cold in this bar, and that's where I first met Natalie. But the day before we met in this ice cold bar, she gave her lecture. Out comes Natalie, 2004, hair, clothes. Natalie never walks quietly into a room. And she gave this absolutely fantastic lecture on polymer physics. And so when I met her in the bar the next night, the first thing I said to her was, when are you moving to Imperial? It was painfully obvious to me that this is where she was going to come. It was destined. Donal was not going to allow her to sit down the road at Queen Mary. I'm sorry, Queen Mary, but if there's anyone here, you weren't going to keep hold of Natalie. And as I said, she came here and has been phenomenally successful in a very, very short period of time. And clearly, there's so many people here that respect her work because we've come from such a long, long way away. So what else can I tell you about her? Well, she speaks many, many languages. And the funny thing is she kind of uses them all at the same time. She kind of generally speaks English, but then every so often she'll throw in a word that we all have to understand. So you'll find that most of us sign off on our emails saying ciao, because Natalie does. And when we drink beer, we don't say cheers. For some reason, we say chin chin. But the only thing that Natalie reserves, well, the only thing that I know about, because I don't know how you swear in other languages, but she reserves the English language for swearing. And Adele's pretty good at this, but Natalie had that perfected a long, long time before. In fact, when she went to Cambridge, she had a few choice words, and she was talking in the lab one day, and someone tapped her on the shoulder and said, you know, Natalie, you should really tone it down a bit. But I absolutely love the way she said, bloody hell. She's the only person I know where bloody hell doesn't actually sound that bad at all. So, I think we ought to leave. The little Google list that I found said, don't go on because, you know, people want to get away. But the last thing they have to remember is the speaker, not you, Gary. You have to slide away. So what do we remember about Natalie's presentation, which was really, truly excellent, and I think is a wonderful insight into the world of polymer science. However, we started off by thinking that plastics and polymers were cooked spaghetti, and now we know that sometimes they're cooked spaghetti with some uncooked spaghetti, and sometimes cooked spaghetti with some al dente spaghetti mixed in. So the next time you're in an Italian restaurant, you get a bowl of spaghetti that maybe cooked well or not cooked well, you might want to call the waiter over and say, I have a friend who works in the field of polymer science. And she taught me all about the solid state microstructure of polymers. And this bowl of spaghetti isn't right. So just think of your next plate of spaghetti and think solid state microstructure of polymers, because that really is what Natalie has brought to the field. Something that Donal said in the 90s, we don't know enough about it, and I think there's many of us here who have really benefited scientifically from now appreciating the subtleties of polymers in our field. So with that, I will say goodbye, and thank you again, Natalie. That was wonderful.